Thanks to everyone that is still listening. So I start with the following problem. I have a closed orientable surface, closed meaning compact without boundary. On such a surface, I have a notion of algebraic intersection. Sorry. What? Okay, so how do I point? Okay, no. No. Okay, so on an orientable surface, I have a notion of algebraic intersection. Here I have two closed curves, alpha and beta, and I say that at every intersection point, let's assume that they intersect transversally. At every intersection point, I give a sign, which is +1 if alpha crosses beta from left to right, and -1 if alpha crosses beta from right to left. So of course it depends on the order of alpha and beta. It is antisymmetric. So it is antisymmetric, and actually it only depends on the homology classes of the closed curves. So it induces a symplectic bilinear form on the first homology of our surface. And now I'm going to assume that my surface has some metric, let's say good enough so that you can compute lengths and volumes. And I'm interested in the following quantity. So I take the supremum of the algebraic intersection of alpha and beta over all pairs of closed curves alpha and beta divided by the product of the lengths. This gives me some quantity which only depends on the surface and the metric. And to make it invariant under dilation, I multiply by the volume. So for those of you who know the systolic volume, it's a bit like a tame cousin of the systolic volume. So why would anyone be interested in such a thing? One motivation, my original motivation, was that it comes up as a comparison constant between two natural norms on the homology. One is the L2 norm, the Hodge norm, which I assume all of you know, and another is the stable norm, which in a sense measures the length of a homology class. So it's in this context you can view it as the L infinity norm. And so those are two norms on a finite dimensional vector space. So they are equivalent. And the question is, what are the comparison constants? And the answer is this quantity, which I have denoted k-vol, comes up as a comparison constant. By the way, this quantity doesn't really have a name. So if anybody has something to suggest, I'm open to all suggestions. So sometimes I'm going to call it Bill, which is as good a name as any. And another motivation is that it is a bit like the systolic volume, but less wide. You're going to see in a minute why. And so the first question is to study this bill as a function of the metric when you fix the genus. An easy remark is that it is easy to make it go to infinity by just pinching a curve. So here the red curve, you can imagine it is infinitely small and the volume is not zero. So obviously the bill goes to infinity. So it's never going to be bounded from above. Question, can we bound it from below? So there's a general problem. Try to find the infimum or maybe the minimum of this quantity over all possible metrics. So we can actually say something about this problem. Bill is always greater than or equal to 1, and it is equal to 1 if and only if the surface is a flat torus. Okay, so we have the answer. And now the question would be, let's fix some genus, say 2, and can we find the minimum? And then, assuming we have found the minimum for all genus, could we find an asymptotic estimate of the minimum as a function of the genus when the genus goes to infinity? And of course, our secret hope would be that it would behave more or less like the systolic volume, which is in genus over log squared of the genus. So why did I say that it's tame cousin of the systolic volume? So here you remember, maybe you'd like to know what the systolic volume is? It's okay? Okay. So you remember that the systolic volume of tori is minimized by two special flat tori, or one special flat tori, which is the hexagonal torus. So you see this theorem and you think, okay, maybe the bill is like the systolic volume, only less selective. So what we are going to do, we try to minimize bill, and then among the minimizers of bill, maybe we find the minimizers of the systolic volume, which, as you know, is a very hard problem for all genus greater than 1. Oh, sorry. I can get used to this. Okay. So, of course, even this is much too hard for me. So I thought I would specialize to some, at least it was definitely too hard as a PhD subject. So I thought we would specialize to some special surfaces, which are translation surfaces. So who needs a reminder what translation surfaces are? Okay for everyone? Theo, Valdo? Okay, so systolic volume. You know what the systole is. The systole is the shortest length of a closed geodesic on a surface. So you can try to find the minimum of the systole as a function of the metric. And of course, it's not very interesting because you can dilate the metric. So you take the square of the systole and divide it by the volume to make it dilation invariant. And the systolic volume is the inverse, is a reciprocal of this quantity. It is the volume over the square of the systole. So you see, it's much like my bill, which has a volume and a product of lengths downstairs. Okay? And translation surfaces are surfaces which have an atlas which consists of maps which are translations. Better way to look at the translation surface. What is a translation surface? It is some polygon in the plane whose sides are pairwise, parallel, and with the same length. So you can glue pairs of edges parallel and with the same length, and you get some surface. So an example is this. And in fact, I'm going to specialize even more to surfaces which are tiled by 3 parallelograms. Example. Such surfaces make up what Vlad Markovich called a Teichmüller curve, which is a complex curve in the moduli space of genus 2 in this case. Why is it a complex curve? Because when you have a surface, a translation surface, you can act on it by GL2R or SL2R if you want to preserve the volume. And the orbit of a surface under SL2R is a complex curve in the moduli space. And here, the action of SL2R is very easy to see because you act by SL2R on some parallelogram, gives you another parallelogram, and the sides, the edges, are still pairwise parallel and with the same length, so you can glue again and you get another surface. So it can happen that when you act by an element of SL2R on a surface, say, I start with this and I act by some element of SL2R and I get this. But it could happen in that the surface that I get when gluing the edges of this is actually the same as this. Because this surface could have what we call affine symmetries. Affine symmetries are a group, a subgroup of SL2R, and this group is called the Vich group of my surface. So I'm going to call L3 the surface which is tiled by 3 squares. I'm saying that the Vich group of this surface is generated by 2 matrices or 2 Möbius transformation, one of which is minus 1 over z, and the other is a translation by 2. So why is that? So, proof of the fact that minus 1 of z preserves this surface. So minus 1 of z as a matrix is so this is the element of SL2R which is associated with this Möbius transformation. So as a linear map, it is only the rotation by pi over 2. So I take this surface and I rotate it by pi over 2. So you see that the Greek letters, which label the vertical sides, here label the horizontal sides. Then I cut along the red dotted line. I take the left square and glue it on the right. And you see that I have the same surface, only the names of the edges have changed. So this matrix actually preserves this surface. Okay, so we have one generator of the Vich group. And here is another generator. So I act by so if the Möbius transformation is this, then the matrix is this. So I act on my template by this matrix. I get this. I cut along the dotted lines, glue back on the left what I cut from the right, get these other surfaces, cut again, glue again, and get the same surface. And now, these 2 matrices generate a subgroup of SL2Z which has index 3. So either my Vich group is the whole of SL2Z, or it is this group, and it is easy actually to see that it's not, the Vich group is not the whole of SL2Z, because this matrix is not in the Vich group. I'm almost sure it's 3. Because you have this one, the other one, and the identity. Yeah, so. Okay, so now I have computed the Vich group of my surface. So what I'm going to look at now is what is called the Teichmüller curve of this surface. Yeah, sorry, I should explain a bit better. So you know that, okay, I'm considering surfaces modular isometry because everything I'm interested in is invariant under isometries. So what is the group SL2R quotiented by isometries? This is a hyperbolic plane. So what I call the Teichmüller curve of my surface is the quotient of the hyperbolic plane by the Vich group, which is a Fuchsian group by construction, more or less. So what is the Teichmüller curve of my surface? Here it is. So this is a fundamental domain. Recall that I have 2 generators in my Vich group. One is a translation by 2, which glues the left vertical side to the right vertical side. And another one is Z2 minus 1 over Z, which glues 1/2 of the half circle to the other half. And my surface corresponds to the point I. It is invariant by the rotation by 2. I have other surfaces, other interesting surfaces in this Teichmüller curve. No. Okay, so this is the fundamental domain, and this is what it looks like. What it looks like after the identifications. So in this corner, you have my surface with 3 squares. So this can be viewed as a space of translation surfaces which are tied by 3 parallelograms. Okay. The L3, the surface with 3 squares, is not the only interesting surface in this Teichmüller disk. You have another one, the point A on the left side is this surface on the right, which is also this one. So beware that here the identifications have changed because the left horizontal side is glued to the lower right horizontal side, so there is a cross. Okay, not sure how to say it. So it is actually also this surface because you can cut the lower left square and glue it on top, and it gives you this. So this is another 3 square surface, and actually it corresponds to the image of my 3 square surface under this matrix. So this proves that this matrix is not in the Witt group because this surface is not the surface L3. So that's another interesting surface if you are interested in square-tiled surfaces. And this one is also interesting. So this one is a point B. It is the only surface. It is the only surface of genus 2 tiled by 6 equilateral triangles. And this surface has a very interesting property that it minimizes the systolic volume among all translation surfaces of genus 2 with one conical point. It is called a stratum, the stratum calligraphic H of 2. So it's a recent theorem, it minimizes the systolic volume. So of course, you see this theorem and you hope, okay, I'm going to prove that this guy minimizes Bill in its stratum, or at least in its Teichmüller disk. And that's not how it's going to that's not going to happen actually. Okay, so now I'm going to state a few results. Il n'y a pas l'heure ici? Elle est juste celle-là? Oui. Elle n'a pas l'air très très juste, non? Okay. So, first result. So, we compute Bill for this three-square surface, and we give the maximizing pairs of curves. So the red lines are the maximizing pairs. So there are a few of them. Okay, so far so good. Yeah. These are all the maximizing pairs, because if you act by the Witt group, of course you're not going to change the intersections, but you are going to change the length. So these are actually the maximizing pairs.
If you act as an automorphism to the structure, for instance, you can pass from one to the other for the last.
Yes. Okay. So you are saying that I should specify the order of the pairs, maybe?
Maybe.
Okay.
No, because that's the question. So in general, what you expect if there are several pairs of curves?
No, in general, I expect only one. This surface is special because it has many symmetries, many self-isometries actually. So. Okay, and now we're going to try to compute Bill over the whole Teichmüller disk of this surface. So the result is very long to state, so I need a bit of notation. First, these two horocyclic neighborhoods of the cusps of my Teichmüller disk are going to play some parts, so I give them a name. So it's V1 and or V minus 1. Okay, now it gets hairy. There is a special set of geodesics on my surface, on my Teichmüller disk, which are going to play a special part, and I give them a name. So you take all geodesics with integer endpoints. Integer includes infinity. Infinity is an integer. And then you act by the Witt group on this set of geodesics. And I call this calligraphic Z. In particular, it contains the vertical lines which start at 1 over n for any integer n. So that's a lot of lines, but it's not dense. That's the point. Its complement contains many open sets. Okay, so the result, and you see it keeps getting hairy. So I'm not even going to say the value, but we get the minimum, and we compute the surfaces at which the minimum is achieved, and we determine the behavior of Bill at infinity in the Teichmüller disk. So the Teichmüller disk, remember, it has what? It has two cusps. So this one is the point 1 or minus 1 below, and this one is infinity. So the result is that when you go to infinity in this cusp, Bill goes to 3, which is the value at the corner, and when you go to infinity in this cusp, Bill goes to infinity. And furthermore, the set of geodesics Z is a set of local maxima of Bill. So the value is always 3 when you are in this set of geodesics. Okay, so this is a very uninteresting statement. But at least something should be pointed out. You see that the interesting surfaces, that is the two three-square surfaces and the equilateral triangle surface, they are not at all minima of Bill. On the contrary, they are local maxima because they are you see that the three-squared surfaces are on some red lines, and so is the 6 equilateral triangle surface. So those surfaces have Bill equals 3. So they are definitely not minima. And what? Je comprends rien. And on the other hand, the minima are surfaces which do not look interesting at all. Unless something, I missed something, but maybe. So now I'm going to try to explain, because the proof is actually more interesting than the theorem. So again, some notation. So I'm going to call T of xy the torus, which is the quotient of R2 by the lattice with one unit vector and the vector PQ, xy, sorry. So this is the torus T of xy, and so the surface x of xy is just the surface tiled by 3 copies of this parallelogram, and on this surface I say that a curve has direction PQ if it projects in the torus to a curve which is p times this vector plus q times this vector. Okay. Nothing special. So observe that if you take a rational slope, PQ, you have always three what is called the saddle connections, that is geodesics with which go through the singular point, the conical point. So I have drawn them in the case of zero slope, of infinite slope, and of slope equals 1. So my surface is a threefold ramified cover of the torus. So each geodesic lifts to 3 geodesics in the surface. And an interesting property of this surface, this is a very special surface, is that all those geodesics always have the same length. So in fact, what I'm looking for is the maximum of this quantity. So downstairs you have the product of the lengths, and upstairs you have the algebraic intersection. And you are taking the supremum over all pairs of rational slopes. Of course, when you have chosen 2 rational slopes, you still have to take the maximum over all 9 pairs of geodesics with this slope. The 9 pairs of geodesics of respective slopes p over q and p prime over q prime, they have only fixed amount of intersection to share between them all. So what you want, if you want to maximize intersection, is you hope that for some special slopes, maybe, the intersection will concentrate on some special pair of geodesics instead of equidistributing over all 9 pairs. So you wonder what could be the pairs of slopes for which the intersection concentrates on some pair of geodesics, and so here are examples. So in this case, I take one slope is 0, the other one slope is infinity. Well, one slope is 0, the other one is infinity, and you see that you have the determinant is 1, and you have 3 pairs of geodesics such that the absolute value of their intersection is precisely equal to the determinant. So you might wonder why these 2 ones on the left have 0 intersection. The idea is that in the surface, so I'm going to use colors. So those 2 curves, they intersect as sets, but not transversally. They do not intersect as homology classes. So they touch at this point, but they do not intersect. So I prepared a talk for specialists, so I thought I could use the sentence, if you have read Macmillan's such and such paper, but forgive me. So what Macmillan proves, let me tell the whole story. So 20 years ago, Veitch proved that there is a special class of curves of translation surfaces, which are called Veitch surfaces, for which either in some fixed direction, either all geodesics are equidistributed or they are all periodic. And it is rather easy to see that for all square-tiled surfaces are Veitch surfaces. So on the square-tiled surfaces, if you fix a direction, either this direction is rational and then all geodesics will be closed in this direction, or it is irrational and then all geodesics will be not only dense but equidistributed. And so the next question, if you will, is now let's take rational directions with the denominator going to infinity. And is it true that the closed geodesics in this direction are going to equidistribute? And it turns out that the answer is no. I'm not even going to attempt a drawing, but you can find beautiful drawings in a paper by Samuel Lelièvre. And Diana Davis. I forget the title, but it has golden L in it. And they produce striking pictures of very long closed orbits in some surface, which avoid some part of the surface. And so it is not true that in general a very long closed orbit is equidistributed in the surface. And actually, what Macmillan proves is that the longer the continued fraction expansion of P sur Q, the more equidistributed the closed orbits will be. So now the idea, what we want for our purpose is to find closed geodesics which do not equidistribute. So what we need is directions, P over Q, which have the shortest possible continued fraction. So those are the and those are precisely yeah, okay, sorry. I'm going back to my drawing of the set Z. So now I'm going to explain why this strange set of geodesics is. A geodesic in the hyperbolic plane has two endpoints, and each geodesic is associated to a pair of slopes in the surface. So for instance, let's take the vertical line from 1 to infinity. So that corresponds to surfaces, translation surfaces, tiled by 3 parallelograms, in which the geodesics with infinite coslope are orthogonal to the geodesics with coslope equal 1. Or for instance, no, easier maybe. So here is my surface, which corresponds to point I in the hyperbolic plane. And I take the Teichmüller geodesic, which contracts this length and expand this length. So I get a surface which is like this, maybe. And this corresponds to a surface which is here. And when I squeeze this direction and extend this direction, I move on this geodesic. So this geodesic in the hyperbolic plane is the locus of translation surfaces in my Teichmüller curve, such that the infinite coslope and the zero coslope are orthogonal. Okay. So this is why this strange set of geodesics comes into the picture. Okay, but now that's the story that you tell children, but actually the things do not happen that way, and you have to fight. That's life. So if we are going to generalize this result, we definitely need to find some quantitative equivalent of Macmillan's theorem. Okay, but assuming we have done that, now all we have to do is find the minimum of this quantity. And this can be this can be done by a geometric construction because this quantity is actually easy to see on a picture. So here you have the geodesic. So R and R prime are P over Q and P prime over Q prime. The black geodesic is a set of surfaces such that the curves in the translation surface with slope R and R prime are orthogonal, and the red lines are not geodesics; they are an equidistant set from the black geodesic. So they correspond to surfaces on which the curves with slope R and R prime are not too far from being orthogonal. And so this equidistant set has an angle with a geodesic, which I call theta. And this ugly thing over there is just the cosine of theta. So it is actually easy to visualize. And so what we do now to compute this bill, we take a surface which we view as a point in the Teichmüller disk. We look for the closest geodesic in Z. and we take the equidistant set through our point, compute the angle, take its cosine, multiply by the volume, and we get the bill. That's, yeah, I should go back a little bit. So, for instance, the surface you see that here you have 5 different maximizing pairs, but all of them have either coslope 0 and coslope infinity, or coslope 1 and coslope -1. And that corresponds to the fact that my surface, which is point I, lies on 2 geodesics in Z, one of which is the red circle, and the other one is the vertical geodesic. So the vertical geodesic corresponds to coslopes 0 and infinity, and the red circle corresponds to coslopes 1 and -1. Oh no. And okay, so now we know how to compute the bill of any surface, and if we want to minimize bill over the Teichmüller disk, what we need to do is to find a point in the Teichmüller disk which is as far as possible from all geodesics in the set Z. So this can be done by elementary geometry. Okay. No. First, you observe that if you go far up in the cusp, the regions become very small. So what the interesting stuff is going to happen close to the lower boundary. You observe that close to the lower boundary, the regions of the complement of Z are triangles, and to find the point of the inside of a triangle which is as far as possible from the boundaries, you take the bisectors of the sides, and the intersection of the bisectors gives you the center of the in-circle, and that's the point which is furthest from all sides. So that's elementary geometry. And this is so, I should zoom, but you see some point K. It is Smile made color drawings of the banana neighborhoods, and you see that the point K lies on the boundary of 3 banana neighborhoods, which are chosen precisely so to have the right angle. So this point is the minimum. Not that it has anything interesting, but how much time do I have?
You have 10 more minutes.
Okay, good. Perfect. So far, I have proved that I have found the minimum. I have shown how to compute k-vol, and we have seen that it equals 3 on some set of geodesic which go, and in particular, since the cusp gets narrower and narrower when you go to infinity, it's easy to prove that you tend to 3 when you go to infinity in the upper cusp. But from what I have said, you may have the impression that Bill is bounded on the Teichmüller disk. So, so it seems that I'm lying. So I have lied a little bit, actually. But in the statement of the theorem, you remember that if you go to infinity in the lower cusp, Bill goes to infinity. So I have been lying at some point. So here is how I lied. In all these computations where you had huge formulas with P, Q, and P prime and Q prime, I always assumed that PQ was different from P prime, Q prime, Q prime. But what happens if PQ equals P prime, Q prime, Q prime? So you are going to tell me, in this case, the geodesics are parallel, and parallel curves do not intersect, so they do not have any algebraic intersection, so nothing happens. And that would be wrong, actually. For instance, in this surface, the green geodesic and the red geodesic have the same direction, obviously, which is 1, 1, and they do intersect. Why is that? Well, here you had two geodesics with the same direction, because this is actually pi, which did not intersect. And now, we have another configuration. So this is a local picture at the singular point. This is a singular point, and all of those angles are pi. I have a total angle of 6 pi at my singular point. And here you see that those curves are actually parallel because their angle is pi, but they do intersect. Okay, so that's a fact of life. Of course, if two parallel curves are going to intersect, they cannot intersect more than once at the conical point. So in general, this is not going to give you a lot of intersection. But still, if those curves are very short, it could still make for a big bill, if you will. And when are those curves very short? They are short when the denominator here is small. And you see that actually the level sets of this function are actually horocycles centered at minus p over q. So when you get close to 1 or minus 1 in this horocycle, the denominator, which I had on the previous slide, becomes very small, and so Bill gets big, and that's how Bill can tend to infinity. And that's all.
Okay, thank you very much. Do we have any questions?
please.
Does it make sense to make the same analysis for each group that are not matrices instead to
As you saw, going for this question.
Can you repeat the
It looks
question,
like it looks like
Daniel,
a setup.
so that the others listen? Can you repeat the question, please?
Okay, so R1 was asking what happens when we consider Vich groups which are not lattices. That was your question? What's going to happen in this case is the Teichmüller curve is going to be dense in something. It's not going to be closed. What I think in this case, what you should do is so even though your Vich group is not a lattice, your curve, your surface, no. Your surface will still have some cylinders of periodic curves, and in the hyperbolic plane, this cylinder is still going to give you some slope, and actually you take the slope of the periodic curve and the slope of this saddle connection. This is going to give you a pair of slopes and hence a geodesic in the hyperbolic plane, along which you can at least estimate build from below. So if you choose your cylinder correctly, the area of the cylinder should be smaller than half the volume of the surface, and this is going to tell you that along this geodesic, B is going to be larger than 2. And you can always find a cylinder whose area is smaller than half of the volume, because assume you have a very big cylinder, assume it is like this, so it is more than half the surface, then you can find another cylinder which is going to be very small, which means that along some other geodesic, maybe like this, B is going to be very big. And what I would like to do would be to use the fact that directions of periodic cylinders are dense. So I have this dense set of geodesics along which B is larger than 2. So that's the general idea. But it's not so easy, because if I have to change, if this geodesic gives me a bill which is too small, then I have to find this other cylinder. But in fact, I do not know where this geodesic lies. So it could be very far away. So I cannot guarantee that this set of geodesics is going to be dense. That's the difficulty of the thing.
Other questions? Are there questions from the people in video conference?
Anybody there? No.
Okay, so we shall resume in about 10 minutes. Thank you again.